Welcome to Tech with Shaping Pixel. In this video, we're diving into the full crash course and latest real exam questions and answers for the Microsoft Certified Azure Database Administrator Associate DP-300. If you haven't subscribed to our YouTube channel yet, we'd love for you to join our growing community. Just hit that subscribe button. Want a downloadable PDF of these questions and answers? You can grab it from our website, www.shapingpixel.com. Full link is in the description below. Let's get started. Implementing Azure SQL databases. Cloud technology has revolutionized database management by eliminating costly hardware and tedious maintenance. With Azure SQL database services, organizations can focus on their core business, while Microsoft handles the heavy lifting of infrastructure and routine administration. Infrastructure as a Service, or IaaS. Running SQL Server on an Azure virtual machine is the most common infrastructure as a service, or IaaS, approach. This model offers high availability, up to 256 terabytes of storage per instance, and gives you full control over the operating system and SQL configuration. Platform as a Service, or PaaS. Platform as a Service, or PaaS, takes automation further. With options like Managed Instance, Single Database, and Elastic Pool, Microsoft manages hardware, operating system, and database engine. You handle only database-specific tasks, enjoying automatic backups, patching, and high availability. Billing models and service tiers. Azure SQL offers two main billing models: Database Transaction Unit, or DTU, and Virtual Core, or vCore. Service tiers include General Purpose, Business Critical, and Hyperscale, each designed for different performance and storage needs, ensuring flexibility and cost efficiency. Deployment and administration. Deploying Azure SQL resources is simple with tools like Azure Resource Manager templates, DACPack, and PowerShell. Microsoft ensures seamless updates and patches, so your data stays secure and available, letting you scale and innovate without administrative headaches. ARM templates, or Azure Resource Manager templates, let you define Azure resources, like virtual machines and databases, using code written in JSON. This approach allows you to describe your entire infrastructure as code, making deployments more predictable. How ARM templates define resources. A single ARM template can define multiple resources, such as a virtual machine, an app service, and a database. Some resources may reference others, but dependencies matter. For example, a database depends on a database server, while an app service might reference a database but does not strictly depend on it. Benefits and versioning. Using templates ensures consistency and speed. Every time you deploy with a template, you get the same result. By storing templates in your source code repository, you can version them and track changes over time, making collaboration and troubleshooting easier. Customizing deployments with parameters. To deploy the same type of resource repeatedly, each must have a unique name. ARM templates use parameter files like azuredeploy.parameters.json to specify unique properties such as server names and administrator credentials, allowing for flexible and customized deployments. Deploying with PowerShell and Azure CLI. You can deploy ARM templates using PowerShell or the Azure Command Line Interface, or CLI. First, create a resource group, then use deployment commands with your template and parameters to provision resources efficiently and reliably. Business continuity means keeping your organization running even when disaster strikes or operations are interrupted. The two main strategies are high availability, which aims for seamless operation, and disaster recovery, which focuses on rapid restoration after an outage. High availability solutions like always-on availability groups use synchronized replicas of production data. This allows a quick switch to backup systems if the primary fails. These solutions are complex and costly, but they minimize downtime and data loss, making them ideal for mission-critical applications. Disaster recovery approaches accept some interruption but aims to resume normal operations quickly. Log shipping is a classic method, restoring transaction logs to a replica database. It is easier and less expensive to set up, but requires regular updates to minimize data loss. Azure-specific solutions, Azure Site Recovery replicates workloads to secondary locations, while premium availability models synchronize data across multiple servers for better performance. Zone redundant configurations spread data across 3 separate data centers, ensuring resilience even if one zone fails. Backup and restoration features, Azure SQL databases offer automated backups with full, differential, and transaction log backups stored in geo-redundant storage. Temporal tables and geo-replication enable targeted restoration and protection against accidental deletion or regional failures. Azure databases are protected by multiple security layers, starting with network security. This outermost layer blocks unauthorized users and lets you control how data is accessed, whether through a public Internet Protocol address or privately via a virtual network. Firewall rules can be set at both the server and database levels, granting access only to specific Internet Protocol addresses or ranges. Virtual network service endpoints and network security groups allow you to restrict traffic based on Azure tags, such as SQL for Azure SQL databases or App Service for Azure App Service domains. Access management. Access management in Azure lets you define exactly who can access your data and what they can do with it. Role-based access control assigns roles like contributor, SQL contributor, or SQL security manager. Within databases, predefined roles such as database owner, reader, or writer can be customized, giving administrators precise control over permissions. Threat protection and auditing. Azure's threat protection features analyze audit logs for suspicious activity like SQL injection or brute force attacks. SQL auditing records database events to logs, helping with compliance and security. Threat detection alerts appear in Azure Security Center. Data encryption and masking. Azure protects data in transit with transport layer security and at rest with transparent data encryption, which uses the advanced encryption standard algorithm. Dynamic data masking hides sensitive information, such as credit card numbers, from non-privileged users. Fine-grained control and key management. Encryption keys are securely stored in Azure Key Vault, with options for service-generated or user-managed keys. These combined security measures ensure your Azure database remains protected from threats and unauthorized access. Scaling Azure SQL databases is all about flexibility and efficiency. With Azure, you can adjust your database's performance on the fly, allocating more resources when needed and reducing them to save costs when demand drops. Vertical and horizontal scaling. There are 2 main ways to scale, vertically and horizontally. Vertical scaling means boosting resources like CPUs, memory, or storage, or upgrading your SQL Server edition for more features. However, this comes with physical and financial limits. Horizontal scaling spreads workloads across multiple systems, which is especially useful for serving users in different regions. Often, both methods are combined for optimal results. Virtual machine options. Running SQL Server on an Azure virtual machine gives you many configuration choices. You can select from various VM sizes, memory to CPU ratios, and storage types, including mechanical drives or 3 levels of solid-state drives. Features like disk striping and blob cache can further enhance performance. Instance and elastic pools. SQL-managed instances can be grouped in instance pools where each instance has dedicated resources. Azure SQL databases also support elastic pools, letting multiple databases share resources efficiently, especially when their peak workloads occur at different times. Scaling operations and tools. Scaling is managed through the Azure portal, PowerShell, Azure CLI, or the REST API. Tools like the Elastic Database Client Library and Split Merge tool help manage and optimize your databases seamlessly. Data partitioning is all about splitting up your data to make databases faster and more efficient. This can mean dividing data within tables, across databases, or even between physical locations. Why partition? Resource limits like storage size, computing power, and network bandwidth can slow down databases. Partitioning helps overcome these limits, especially for global applications where data needs to be closer to users or comply with local laws. What is sharding? Sharding is a specific type of partitioning. It splits a database into multiple copies called shards, each on a different server. Each shard holds a subset of the data, reducing bottlenecks and latency. Sharding strategies. There are several ways to decide which data goes to which shard. The lookup strategy uses a primary key, directing requests based on something like a tenant ID. The range strategy splits data by ranges, such as dates. The hash strategy uses a hash function to spread data evenly, though rebalancing can be tricky as data grows. Choosing the right approach. The best sharding solution depends on your data and usage patterns. As your data changes, you may need to rebalance shards. Testing and evaluation are key to finding what works best. If your database is currently running on-premise, migrating to the Azure cloud is a crucial step for modernization. Microsoft offers a range of tools to make this process smoother, no matter your starting point or destination. Migration methods. The Azure Database Migration Service, or DMS, is designed to help you move databases from on-premise or other cloud providers to Azure-hosted databases. DMS supports both offline and online migration. Offline migration means your data will be unavailable during the process, while online migration uses continuous synchronization to minimize downtime. Microsoft recommends testing how long an offline migration will take, and if the interruption is too long, switching to online migration. Planning and assessment. Before migrating, use the Data Migration Assistant tool to assess your on-premise SQL Server databases. This tool identifies compatibility issues that could affect your move to Azure. Depending on your destination, whether it is SQL Server on a virtual machine, a managed instance, or Azure SQL Server, you may need to check for compatibility and adjust accordingly. Final steps and considerations. You can also back up your database, copy it to Azure Blob Storage, and restore it in Azure. For ongoing data movement, transactional replication is another option to keep your databases in sync during migration. Migrating your data to an Azure-hosted database opens up new possibilities for scalability and performance. Currently, you can move data from Oracle, RDS SQL, SQL Server, Postgres SQL, and RDS Postgres SQL to most Azure SQL database services. As Microsoft expands support, more source databases will become eligible for streamlined migration. Common migration requirements. No matter which database you are migrating, there are some universal requirements. You need a connection to Azure, either through a site-to-site virtual private network or ExpressRoute, which is a high-speed connection provided by third parties. Ensure network ports 443, 53, 9354, 445, and 12,000 are open and that TCP/IP protocol is enabled. Your firewall must allow database engine access, and if you use a firewall appliance, permit the Database Migration Service, or DMS, to reach your source server. SQL Server to Azure SQL Database. For SQL Server migrations, set up an Azure SQL Database instance and use the Data Migration Assistant version 3.3 or later. Allow DMS through your firewall, typically on port 1433, and create a server-level firewall rule in Azure. Credentials must have control server permissions. SQL Server to Azure SQL Managed Instance. When migrating to an Azure SQL Managed Instance, provision the instance and configure firewall rules for DMS and SMB port 445. Open UDP port 1434 for the SQL browser service. The login must be a sysadmin, and you need a network share for backups. On Azure, set up a blob container and shared access signature URI. If you are planning to migrate your SQL Server to Azure SQL, the version you are currently running plays a crucial role. Upgrading your server instance may be necessary to ensure a smooth transition to the cloud. Preparing for upgrade. SQL Server 2019, also known as version 15X, offers broad support for various upgrade paths. If you are running SQL Server 2012 with Service Pack 4 or later, 2014 with Service Pack 3 or later, 2016 with Service Pack 2 or later, or 2017, upgrading is generally straightforward. Always check the Microsoft website for your specific version and edition to confirm supported upgrade paths and requirements. Application considerations. Once your database engine is in the cloud, you no longer need to worry about service packs or patches. However, databases rarely operate alone. Applications that rely on your database may also require upgrades to function properly in the Azure environment. Migration tools and strategies. Azure provides a wide range of tools and technologies to help you upgrade and test your applications. The migration process will depend on your system's downtime tolerance, application design, and budget. Managing traffic and rollback. Standard backups, geo-replication, DNS name changes, and Traffic Manager can help you control data movement and manage traffic flow during migration, including rollback if needed. Azure SQL and SQL Server Database Task Automation. When managing SQL Server, whether on-premise or on a virtual machine, maintenance is not pre-configured or automated. Regular oversight is crucial to keep your database server running smoothly and efficiently. Backup and recovery. Backups are a cornerstone of disaster recovery. It is important to schedule full, differential, and log backups regularly. This ensures that, in the event of a failure, you can restore your data with minimal loss and downtime. Consistency and performance. Performing regular consistency checks helps catch issues before they escalate. Rebuilding indexes is vital for both online transaction processing and reporting databases, as it maintains optimal performance. Updating database statistics and monitoring for query bottlenecks are also essential. Housekeeping and automation. General housekeeping tasks, such as shrinking logs and databases, can improve performance and reduce storage costs. These tasks require ongoing attention to keep your SQL Server environment healthy and efficient. Azure SQL differences. In contrast, Azure SQL and SQL managed instances automate most maintenance tasks, reducing manual intervention and allowing you to focus on higher-level database management. Many businesses operate with two main data environments. Understanding these environments is key to managing and analyzing business information effectively. Operational and reporting environments. The first environment is operational and transactional, where day-to-day business activities are recorded. The second is the reporting or data analysis environment, which is designed for deeper insights and decision-making. Data movement and transformation. Data is regularly migrated from operational databases to reporting databases. This process often includes transforming, aggregating, and classifying the data. Depending on business needs, this migration can happen daily or even every few minutes. Reoccurring data tasks. Reoccurring data tasks go beyond database maintenance. They include importing or exporting data from external sources and sending notifications when tasks are complete. Some tasks are even triggered by specific data states. SQL Server offers a powerful maintenance plan feature designed to automate routine database upkeep. Whether your databases are hosted on-premises or on a virtual machine, maintenance plans help you schedule and manage essential tasks, ensuring your SQL Server environment remains healthy and efficient with minimal manual intervention. Common automated tasks. With maintenance plans, you can automate a wide range of tasks across selected databases. These include checking database integrity, shrinking databases, reorganizing and rebuilding indexes, updating statistics, cleaning up history, and executing SQL Server agent jobs. Additionally, you can schedule regular database backups and clean up old maintenance tasks, streamlining your workflow and reducing the risk of human error. Preparing for automation. Before using the maintenance plan wizard, there are a couple of important prerequisites. First, you need to enable Agent Extended Procedures, or Agent XPS, using the SP-configure command in SQL Server Management Studio. Setting the value to 1 enables this feature, while 0 disables it. Ensuring successful scheduling. It is also crucial to ensure that your SQL Server agent service is running, and preferably set to automatic startup. This guarantees that any maintenance plans or jobs you schedule will execute reliably, keeping your databases performing at their best. Creating a maintenance plan in SQL Server does not require the wizard. Instead, you can use the graphical interface for more flexibility. By right-clicking on Maintenance Plans and selecting New Maintenance Plan, you gain access to a powerful design environment. Building the maintenance plan. Within this interface, you can create multiple sub-plans. Scheduling is straightforward. Clicking on a sub-plan schedule brings up the familiar Job Schedule window. The toolbox now offers all previous tasks plus extras like Execute SQL statements and Notify Operator task. Setting up your plan is as simple as dragging and dropping tasks onto the design area. After dropping a task, you can select which databases it will affect and even review the SQL statement that will be executed. The options windows display correctly at high resolutions, making this method user-friendly and likely preferred over the wizard. Configuring notifications. Once your tasks are configured, connect them in the desired order using connector lines. To finish, add a Notify Operator task. If you have not set up an operator, create one under SQL Server, then enter the message details. Remember, operator notifications require database mail. SQL Server maintenance plans offer predefined tasks for quick setup, but SQL agent jobs provide even more flexibility. Think of maintenance plans as templated jobs, while SQL agent jobs let you automate a wide range of tasks beyond just maintenance. Automating routine tasks. With SQL agent jobs, you can automate not only backups and index rebuilds, but also routine, non-administrative tasks. Each job can include multiple steps, such as running SQL statements, executing stored procedures, launching SQL Server Integration Services packages, or even running operating system commands using the XP Command Shell feature. Flexible scheduling. SQL agent jobs support multiple schedules. For example, if customer orders arrive between 8 and 10 in the morning, you can schedule a job to run every 5 minutes during those hours. If extra orders come in on Friday afternoons, you can add another schedule to run every 15 minutes from 1 to 4 p.m. on Fridays. Notifications and monitoring. You can set up notifications to alert an operator about the job's outcome, whether it completes, fails, or succeeds. This ensures you stay informed and can respond quickly to any issues. Practical example. For instance, you might create a job to import a CSV file. If it fails, the operator is notified, and upon completion, other staff receive an email with details of the imported data. Managing multiple SQL servers, whether on-premise, in virtual machines, or as managed instances, can be a challenge when it comes to automating maintenance plans or jobs. Fortunately, SQL Server offers a multi-server administration function to streamline this process. Setting up multi-server administration. With multi-server administration, you can designate one server as the master and assign various target servers. This setup allows you to run maintenance plans or SQL jobs across all target servers simultaneously. The key assumption here is that you will perform the same tasks on the same databases across each server, making this feature ideal for generic server administration. Setting up multi-server administration through SQL Server Management Studio is relatively straightforward, but there are important steps to consider before you begin. Configuration requirements. If you are managing multiple SQL Server instances on different machines, you must ensure that the account used by SQL Server Agent is a member of the local Windows Administrator group. Additionally, there are registry settings related to proxy and encryption that need to be adjusted. These configurations are essential for secure and effective multi-server management. Final steps and demonstration. Once these requirements are met, you can proceed to SQL Server Management Studio to complete your setup. In the demonstration, we will walk through these registry changes and show you how to automate your maintenance plans efficiently. SQL Server Policy Management is a powerful feature that lets you create complex rules to enforce standards across your servers and databases. These rules, known as policies, help maintain consistency and compliance. How policies work. A policy is built from conditions which define the specific server objects, called facets, that the policy targets. Conditions use expressions ranging from simple statements like checking if a table name matches a value to more complex SQL-based logic. This flexibility allows you to tailor policies to your organization's needs. Policy evaluation modes. Policies can be evaluated in several ways. You can trigger them manually, schedule them to run at set times, or have them respond to changes in the server. However, not all policies support evaluation when a change occurs. Every policy can be checked on demand or on a schedule, but only certain facets support the on-change prevent mode. Implementing SQL Server policies. To fully utilize policy management, ensure advanced server properties like allowing triggers to fire others are enabled. With these settings, you can effectively implement and enforce SQL Server policies. Backing up your SQL Server instance on a virtual machine does not have to be complicated. While traditional methods like SQL Server Management Studio or Remote Desktop are available, Azure Recovery Services Vault streamlines the process. Backup policies and scheduling. With Azure Recovery Services Vault, you can create backup policies, which are essentially backup schedules. These policies allow you to automate full, differential, and transaction log backups across multiple databases and virtual machines. Full backups can be scheduled daily or weekly, while differential backups can run daily except on full backup days. Transaction log backups offer even more flexibility, running as often as every 15 minutes. Restoring your data is just as simple. Azure Recovery Services Vault enables point-in-time restores, letting you recover your databases precisely when you need them. Azure Backup is a powerful solution for protecting your SQL Server data, whether your workloads are in the cloud or on-premises. Setting up Azure Backup. When configuring backups, you can choose Azure as your backup goal. There is also an option for on-premises workloads, allowing you to use the Azure Backup Service to protect various types of data, including SQL Server. Azure Backup Server details. To enable this hybrid backup, you will need to download and install Microsoft's Azure Backup Server on your on-premises machine. The installer is a substantial 4.2 gigabyte download. This generic solution offers similar functionality for SQL Server as it does for virtual machines. Azure Automation Service lets you create and run scheduled tasks for any Azure resource. You can define these tasks using a graphical interface or with a PowerShell script, making them as simple or complex as needed. Automating Azure SQL tasks. When automating tasks for Azure SQL, credentials are essential for connecting to your server and database. Scheduled jobs can execute specific actions, like running a stored procedure at set times. This is especially useful for managing important customer data or routine database maintenance. Creating a runbook example. To automate a stored procedure in Azure SQL, you would create a runbook in Azure Automation. This runbook contains a PowerShell script that connects to your database and executes the procedure on a schedule, streamlining your workflow and ensuring consistency. Moving from on-premise SQL Server to Azure SQL Database can feel unfamiliar, especially when it comes to job scheduling. Many database administrators and developers miss the flexibility of scheduled jobs. To address this, Microsoft introduced Elastic Jobs, bringing familiar automation to the cloud. How Elastic Jobs work. Elastic Jobs in Azure SQL Database allow you to schedule and automate tasks across multiple databases. The Elastic Job Agent service, currently in preview, is database-driven and uses tables and stored procedures hosted within a database. It can be hosted only on databases with a service level of S0 or higher, and it targets any Azure SQL database except managed instances. From the host database, you can define jobs that apply to all databases in a target group, making management efficient and scalable. Credentials and target groups. To run Elastic Jobs, you need credentials. The refresh or master credential logs into the target server and queries the master database. A separate job credential executes job steps. These credentials must exist on both the host and target servers, and you can use different credentials for each job step if needed. Getting started. By default, all databases on a server are included as targets. If you want to exclude any, you must do so explicitly. Elastic Jobs bring powerful, flexible automation to Azure SQL Database. Automatic tuning in SQL Server and Azure SQL helps keep your databases running smoothly by optimizing performance behind the scenes. There are two main types: query plan correction and automatic index management, each with its own unique benefits. Query plan correction. Query plan correction, introduced in SQL Server 2017 and available in Azure SQL, monitors query performance using metrics like CPU load, input and output operations, and execution time. If it detects a regression, which means performance has dropped, it automatically reverts to the last known good plan. This process is called forced last good plan and helps maintain consistent performance. Automatic index management. Automatic index management is exclusive to Azure SQL and Azure SQL Managed Instance. It uses artificial intelligence to analyze database performance and can automatically create or drop indexes. If an index is underutilized or negatively impacts performance, Azure SQL will remove it, provided the feature is enabled. How automatic tuning works. Automatic tuning only activates when the database is not under heavy load, ensuring it does not degrade performance during peak times. Query plans are reevaluated after statistics updates or schema changes to adapt to evolving data. Key differences and AI in Azure SQL. Azure SQL leverages artificial intelligence and cloud-scale analysis, learning from thousands of databases to make smarter tuning decisions and deliver optimal performance. When running SQL Server on an Azure virtual machine, managing updates is your responsibility. Fortunately, Azure offers a way to simplify this process by allowing you to configure automatic patching for both Windows and SQL Server during the initial setup of your virtual machine. How automatic patching works. Automatic patching lets you define a maintenance window by specifying the day, time, and duration when updates can be installed. This is important because critical and important updates may require server restarts. By choosing the maintenance window, you can minimize disruption to your operations and ensure updates happen at the most convenient time for your business. Manual updates and PowerShell configuration. It is important to note that automated patching only covers important and critical updates. Other updates or service tasks must be applied manually. For advanced users, Azure also supports configuring automated patching through PowerShell using the command new azvm sql server auto patching config, where you can set the day, time, duration, and patch category for your maintenance window. Azure Database Performance Tuning. When most people think about database storage, they picture the hard drive where all the data files are kept. But there is more to it than just a place to store information. The way storage is managed can significantly impact database performance and reliability. Speed and volume trade-off. Two key attributes of storage are speed and volume, also known as capacity. These two factors often have an inverse relationship when it comes to cost. If you want faster storage, you may have to compromise on how much data you can store for the same price, and vice versa. The importance of backups. Storage is not just about live data. It also includes where you keep your database backups. Regular, full, differential, and log backups are essential for a strong disaster recovery plan. However, the backup process can affect database performance, so it is important to consider the speed of your backup storage as well. Backup storage considerations. Backups tend to use a lot of disk space, but are rarely accessed. Because of this, it is not practical to spend heavily on backup storage, especially for data you hope never to need. Cloud-based database storage. These storage considerations mainly apply to databases running on virtual machines or on premises. Cloud platforms like Azure SQL and SQL-managed instances offer managed environments designed to optimize performance for your specific workload and service tier. Storage performance starts with hardware. In the past, hard drives, or HDDs, used spinning platters, and their speed was measured in revolutions per minute. Today, solid-state drives, or SSDs, have changed the game with faster, more reliable storage. HDDs vs. SSDs. HDDs are still used for high-volume, low-performance needs, spinning at speeds like 5,400 or 15,000 revolutions per minute. SSDs, on the other hand, have no moving parts and are measured by how many random read and write operations they can perform each second. Both types come in different performance levels and price points. Key metrics explained. When choosing storage, focus on three key metrics: IOPS, or input-output operations per second, which measures how many reads and writes happen each second; throughput, the amount of data transferred per second; and latency, the delay before a read or write begins. Different workloads prioritize these metrics differently. Azure Disk Options. Azure Managed Disks offer options from standard HDD for basic needs to UltraDisk for top performance. Higher input-output throughput and lower latency mean higher costs, so balance your needs and budget. Practical tips. Monitor your disk performance using tools like Performance Monitor and always allow extra headroom for peak workloads. Most hard drives include a built-in memory cache, a few megabytes of high-speed RAM. This stores recently written and read data, allowing disks to perform faster than their physical limits. What is blob cache? Azure Virtual Machines, or VMs, feature blob cache, which uses both the machine's RAM and local solid-state drive, known as the D drive on Windows VMs. Blob cache provides high-speed read caching for database operations, making it similar to a hard disk cache but much more powerful. Blob cache availability. Blob cache is only available on high-scale virtual machines paired with premium solid-state drives. This combination delivers enhanced performance for demanding workloads, especially those requiring rapid access to frequently used data. When it comes to maximizing disk performance, you are not limited by the speed of a single hard drive. By writing and reading data across multiple drives at once, you can significantly reduce input and output bottlenecks. This technique is known as RAID 0, or disk striping in Azure. How disk striping works. RAID stands for Redundant Array of Inexpensive Disks. In traditional environments, RAID 0 splits each read or write operation among several hard drives, allowing them to work together simultaneously. In the cloud, this is called disk striping. The operating system manages this process, so applications see one unified volume. Benefits and management in Azure. Disk access is much slower than CPU or RAM, so having multiple drives working together greatly boosts performance. In Azure, higher RAID levels for redundancy are not needed because disk replication already protects against failures. To set up disk striping, use the Storage Spaces utility in Windows to combine disks attached to your virtual machine. Practical considerations. Azure documentation highlights disk striping with premium solid-state drives, but you can also stripe with standard solid-state drives and hard disk drives. However, disk striping is not available with UltraDisks. For the best performance, you may need to experiment with different disk types. When managing SQL Server files, following best practices can make a significant difference in both performance and maintenance. Let us explore how to optimize your file setup for efficiency and reliability. Optimizing file placement. Start by placing your data files and log files on separate volumes. This reduces input and output disk contention, improving overall performance. Enable read caching on the data file volume, but disable all caching on the log file volume to ensure data integrity and optimal write performance. Managing multiple data files. If disk stripping is not an option, but you have multiple disks, consider using multiple data files. Placing these files on separate disks can enhance input and output performance. SQL Server uses a proportional fill algorithm, distributing data evenly across files, which is similar to file stripping managed by the database engine. File growth strategies. Avoid setting auto-growth with no limit. Instead, set a maximum file size just below your disk's capacity. This prevents unexpected disk full errors and allows for better control over storage. Maintenance and monitoring. Multiple smaller files make maintenance easier, especially as databases grow beyond hundreds of gigabytes. Set up alerts to notify you when files approach their maximum size, ensuring you stay ahead of potential issues. Instant file initialization is a feature in SQL Server that helps reduce the time it takes to allocate disk space during file growth events. By default, SQL Server fills new file space with zeros to erase any leftover data, which is mainly a security measure. How it works and when it applies.
File initialization occurs during several operations: creating a new database, adding data or log files, increasing file size, auto-growth events, and restoring databases or file groups. This process ensures that any previously deleted information is overwritten, maintaining data security. However, this zeroing process can slow down performance, especially during large file growth events or database restores. Checking and enabling the feature. To check if instant file initialization is enabled, you can run the xp_read error log command with the search term database instant file initialization, or query the instant file initialization enabled field in sys.dm_server_services. To enable it, add the SQL Service account to the Perform Volume Maintenance Tasks policy under Local Policies, User Rights Assignment in your local security policy. Benefits and Microsoft's recommendation. Enabling instant file initialization significantly speeds up disk space allocation, improving auto-growth performance. Microsoft recommends enabling this feature, stating that the performance benefits far outweigh any potential security risks.
TempDB is the working memory of your SQL Server, handling temporary objects and intermediate results. Its configuration is crucial for performance and stability, especially in production environments where workloads can be unpredictable and demanding. TempDB placement. For optimal performance, place TempDB on its own dedicated drive or volume. The local solid-state drive D is preferred because it is fast and non-persistent, but never use it for data or log files. If the D drive is too small, consider using a striped premium solid-state drive pool with read caching enabled. This separation ensures that if TempDB fills up, it will not impact your main data or log files. Sizing and configuration. When configuring TempDB, avoid enabling autogrow, as growth events can hurt performance. Instead, allocate enough space up front. Match the number of TempDB data files to the number of CPU cores, up to 8 files. This helps prevent file contention, as each core can access its own file. Make sure all files are evenly sized and use 80 to 90% of the available drive space. Best practices recap. To sum up, isolate TempDB, size it appropriately, and align the number of data files with your CPU cores. These steps will help ensure your SQL Server runs smoothly, even under heavy workloads. When setting up SQL Server in the cloud, understanding the relationship between virtual machines and storage is crucial. While storage is vital for databases, the capabilities of your virtual machine, or VM, can set important limits. Virtual machine features and limitations. Not all virtual machines are created equal. Features like blob cache and maximum input-output operations per second, or IOPS, can vary. Even if your storage can handle high IOPS, your VM might cap performance. For example, a VM may limit IOPS to 1,280, even if your premium solid-state drives can deliver 10,000. Choosing the right VM for SQL Server. For most SQL Server workloads, a general-purpose VM works well. Memory, or RAM, is often more important than the number of virtual CPUs, or vCPUs. However, since SQL Server is licensed per CPU, getting more RAM often means paying for extra vCPUs you might not need. Azure offers constrained vCPU VMs to help balance this. Scaling and storage management. If your workload grows, resizing your VM is straightforward, but does require a restart. Adding more storage is even easier and does not interrupt your service. New virtual disks appear in Windows Disk Management just like physical disks on a traditional server. SQL Server and SQL Managed Instance offer powerful tools for managing critical resources, ensuring that databases perform consistently even when multiple applications are running. By allocating resources strategically, administrators can prevent one workload from overwhelming the system, maintaining stability and reliability for all users. Resource pools and workload groups. Resource allocation begins with resource pools. Each SQL Server instance starts with two pools: internal, reserved for SQL Server's own operations, and default, which handles all user and application connections. Administrators can create additional resource pools, each with specific limits for CPU and memory usage. Incoming connections are grouped into workload groups, which are then assigned to these resource pools, allowing for precise control over how resources are distributed. Classification function and resource governor. Connections are assigned to workload groups based on a classification function, which can use criteria like username. This function can be as simple or complex as needed, provided it does not slow down the login process. The classifier function is selected from a drop-down list in the Resource Governor Properties page, making configuration straightforward. Use cases and flexibility. Resource Governor is especially valuable in multi-tenant environments, ensuring consistent performance across customer databases. However, it can also be used in other scenarios, such as minimizing the impact of background tasks on mission-critical systems, providing flexibility for diverse operational needs. When managing SQL Server service accounts, always use SQL Server Configuration Manager for any changes. This tool ensures that permissions and settings are applied correctly, avoiding potential issues that can arise from using other tools like the Services applet. Service account selection. SQL Server services do not need local administrative privileges. Instead, follow the principle of least privilege. Avoid using built-in accounts such as local system or network service, since these have broad access to local and network resources. Instead, choose accounts with only the permissions required for SQL Server to function. This approach reduces security risks and keeps your environment safer. Domain and virtual accounts. If your SQL Server needs access to network resources, set up a dedicated domain account with just the necessary permissions. Make sure this account is not a member of the Windows Administrator group. Since SQL Server 2008 R2, the default installation creates managed local accounts called virtual accounts, like NT Service, MSS SQL Server. These virtual accounts are easier to manage and follow best security practices. Key takeaways. Always use SQL Server Configuration Manager, avoid excessive privileges, and prefer dedicated domain or virtual accounts. Following these best practices helps keep your SQL Server environment secure and manageable. As SQL Server evolves, new features are often introduced at the database level, giving administrators more control and flexibility. But with each new version, ensuring backward compatibility becomes increasingly important for smooth database operations. Compatibility levels explained. The compatibility level is a critical database setting that determines which features are available to your database. For example, SQL Server 2019 introduced many intelligent query processing features, which are only accessible if your database is set to compatibility level 150. However, you cannot set a database to a compatibility level higher than the server version it runs on. If your server is running SQL Server 2017, the highest compatibility level you can use is 140. Configuring compatibility and features. You can adjust compatibility levels and other database features through the Database Properties window, or by using T-SQL commands like alter database and alter database scoped configuration. For instance, enabling query store or setting the maximum degree of parallelism, known as maxstop, can be done at the database level, overriding server-wide settings for that specific database. Performance and tuning impacts. Enabling Query Store allows for automatic tuning, such as forcing the use of the last good execution plan if performance regresses. Features like last query plan stats and legacy cardinality estimation further help maintain performance and compatibility as SQL Server evolves. Intelligent query processing is a suite of optimization features in SQL Server, first introduced in 2017 and expanded in 2019. When your database compatibility level is set to 150, these features are enabled by default, enhancing query performance through adaptive machine learning. Adaptive joins. One standout feature is adaptive joins in batch mode. Here, SQL Server dynamically chooses the best join type during execution based on the actual number of rows. If the row count is below a certain threshold, a nested loop join is used. If it exceeds that threshold, a hash join is selected, adapting in real time for optimal performance. Table variable deferred compilation also improves performance. Previously, SQL Server assumed a fixed row count, often just one, when optimizing queries. Now, it waits to see the actual number of rows in a table variable, leading to much more accurate and efficient query plans. Approximate distinct count. For massive datasets, approximate distinct count offers fast, resource-efficient results. It quickly estimates the number of unique non-null values, making it ideal for real-time dashboards where speed matters more than absolute precision. Memory grant feedback. Adjusts memory allocation for queries based on previous runs. If a query used too much or too little memory, future executions are automatically tuned for better efficiency. Configuration and wrap-up. Most features are on by default, but you can fine-tune them using database scope configuration commands. When choosing between Azure SQL Serverless and SQL Server on a virtual machine, understanding their differences is crucial for making the right decision for your database needs. SQL Server on VM overview. SQL Server running on a virtual machine, or VM, closely mirrors an on-premise setup, but without the hassle of managing physical hardware. Upscaling resources is relatively straightforward, though not entirely seamless. This approach offers extensive configuration options, making it ideal for those who need control and familiarity. Azure SQL Serverless explained. Azure SQL Serverless, the latest addition to Azure SQL database offerings, takes a different approach. Here, you define minimum and maximum hardware boundaries for CPU virtual cores and storage. The database automatically scales resources up or down as needed, and billing is based on actual vCore and memory usage per second. Key differences and use cases. Serverless databases can pause during inactivity, reducing costs, and are perfect for unpredictable or highly variable workloads. This makes them especially useful for new deployments where usage patterns are unknown, allowing you to observe workload distribution before committing to a fixed pricing model. Downsides and considerations. However, serverless databases can experience startup latency after inactivity, as resources must be provisioned from a shared pool. Disabling auto-pause or increasing minimum resources can reduce this lag, but may offset cost savings. Azure SQL and SQL Server Query Performance Tuning. No matter which version of SQL Server you use, from Azure SQL to SQL Managed Instance or the traditional server, the core process for handling queries remains the same. Let us break down how it works. Query processing modes. The query engine operates in two modes. Row mode processes each row individually, checking if values match your criteria. Batch mode, which relies on column store technology, can handle multiple rows at once, making it faster for certain workloads. Query optimization and indexes. When you run a query, SQL Server breaks it into parts and analyzes table structures, indexes, and index density. Index density measures how unique or shared values are, like a barcode being unique to a product. The optimizer uses this information to choose the fastest, most efficient plan. Query store and performance analysis. SQL Server's query store records query execution details, plans, and statistics. If performance drops, you can use the query store to pinpoint when and why. You can enable it in SQL Server Management Studio or with an altered database command. Azure SQL and final thoughts. Azure SQL offers similar query store features, letting you track resource consumption and performance over time. Understanding these tools helps you keep your SQL server running smoothly and efficiently. SQL execution plans are essential for understanding how your queries run in SQL Server. These plans visually map out each step the database engine takes, helping you pinpoint performance issues and optimize your queries for better results. Types of execution plans. There are three main types of execution plans. The estimated execution plan predicts how SQL Server will run your query without actually executing it. The actual execution plan shows how the query was truly executed. Live query statistics, meanwhile, provide real-time updates as your query runs, letting you watch each operation's progress. Reading and analyzing plans. Execution plans are read from right to left, with each icon representing a different operation. The arrows between them show the flow and volume of data. Clicking on an operation reveals details like estimated costs, number of rows, and output columns, helping you identify expensive steps. Improving performance with indexes. If you notice a table scan at the start of your plan, consider adding an index to improve performance. After creating a suggested index, you may see the plan switch to an index seek, often resulting in significant speed improvements. Query store and retrieving plans. You can access historical query plans and performance data in the query store. By querying tables like Query Store Plan, you can retrieve and analyze past execution plans, even viewing them as graphical XML representations within SQL Server Management Studio. Dynamic Management Views, or DMVs, are powerful tools in SQL Server for monitoring and analyzing performance. These views, along with dynamic management functions, provide a wealth of information about server operations and database states. Categories and key views. DMVs are organized by categories, such as Change Data Capture and SQL Server Operating System views. For performance monitoring, execution-related DMVs are especially valuable. The most important ones include DM_exec_query stats and DM_exec_query profiles, both available in SQL Server and Azure SQL. Using DM_exec_query stats, the DM_exec_query stats view returns detailed information about queries over their lifetime, not just a single execution. It provides data like execution counts, minimum and maximum values, and totals, allowing you to calculate averages and identify resource-intensive queries. Real-time monitoring with DM_exec_query profiles. For real-time insights, DM_exec_query profiles shows live metrics for queries currently running. By providing a session ID, you can track how a query progresses, which is especially useful for long-running operations. Practical example and insights. By monitoring a large insert operation, you can see parallelism and multi-threading in action. Watching row counts and table scans in real time helps you understand query performance and optimize your SQL Server environment. Database indexes are essential for speeding up data retrieval, but not all indexes are created equal. Let us break down the four main types: clustered, non-clustered, filtered, and column store indexes. Clustered indexes. A clustered index determines the physical order of rows in a table.
you can only have one clustered index per table, often tied to the primary key. Clustered indexes are great for read-heavy tables, but frequent inserts or updates can slow things down, as the database must rearrange rows. Using a unique identifier like an identity key helps maintain order efficiently. Non-clustered indexes. Non-clustered indexes are separate from the table, and you can have many of them. Think of them like a book's index pointing to data locations. They speed up queries but require extra storage and maintenance, especially during inserts or updates. Including extra columns in these indexes can boost performance, but at the cost of more disk space. Filtered indexes. Filtered indexes only include a subset of data, making searches faster for specific queries. For example, you might filter out irrelevant values or nulls. However, they have limitations, such as not supporting complex comparisons or being used on views. Column store indexes and final thoughts. Column store indexes are designed for analytics, storing data by columns instead of rows. Each index type serves a unique purpose, so choosing the right one depends on your workload and query needs. Efficient database design is crucial for saving disk space and improving query performance. One key principle behind this is normalization, which focuses on eliminating data duplication within tables. What is normalization? Normalization is the process of organizing data into multiple related tables, rather than storing everything in one large table. This approach reduces redundancy and makes data easier to maintain and query. The process of normalization. Normalization typically follows progressive stages: first normal form, second normal form, and third normal form. Each stage builds on the previous one, ensuring data is stored with minimal duplication while maintaining correct relationships. Real-world example. Imagine a sales database where every customer's details are repeated with each transaction. By normalizing, we separate customers, transactions, and items into logical entities, using unique identifiers to link them efficiently. Benefits of normalization. With normalization, tables use compact integer IDs instead of repeating large text fields. This not only saves disk space, but also improves accuracy and makes relationships between data clearer and easier to manage. Performance comparison. After normalizing sales data, the database size was cut in half and query speed increased dramatically. In one test, a complex query ran in just 1.8 seconds compared to over 43 seconds before normalization. Let us explore column store indexes in SQL, a technology designed to make data analysis faster and more efficient, especially when working with large datasets. How column store indexes work. Imagine turning your data sideways, so instead of reading each record one by one, you read entire columns at once. This is similar to Excel's paste transpose function. In SQL, a column store index stores each column separately, allowing for quick access to the data you need. Row store versus column store. Traditional row store indexes keep all index fields for a record together, making them like mini tables. In contrast, column store indexes store each column on its own page, which speeds up searching and reading, but can slow down inserting, deleting, or updating data. Performance and limitations. Column store indexes are not available in every Azure SQL tier. You need at least service level tier S3, elastic pools with 100 elastic database transaction units, or any vCore configuration due to the compute power required. Real-world example. In practice, column store indexes can reduce data size by a third and dramatically speed up queries. However, they require careful indexing strategies to achieve the best performance, especially with normalized tables. When working with SQL Server, understanding how data is physically stored is key. Most databases use two main files, the MDF data file and the LDF log file, both typically placed in the same directory by default. Database files and file groups.
You can add more data files, especially for large databases or environments with multiple drives. Splitting data across drives can boost performance, as SQL Server is optimized for parallel disk access. Table partitioning basics. Beyond file partitioning, table partitioning lets you distribute a table's data across multiple file groups. This can help reduce contention and improve performance, especially as your data grows over time. Partition functions and schemes. To partition a table, you define a partition function that sets boundaries for your data, then map those boundaries to file groups using a partition scheme. This setup allows dynamic allocation of records as data is inserted. Performance insights and indexing. Horizontal partitioning alone may not significantly speed up queries, but combining it with column store indexes can yield dramatic improvements. For example, query times dropped from 17 seconds to under 2 seconds. Vertical partitioning and final thoughts. Vertical partitioning splits table columns into separate tables, which can also benefit from parallel disk access. However, it increases maintenance complexity and may require more careful query management. SQL Server offers two main types of data compression: row compression and page compression. While both aim to save disk space, they work in very different ways and can impact performance in unique ways. Row compression explained. Row compression works by intelligently substituting data types with smaller versions when possible. For example, a 4-byte integer can become a 2-byte integer if the values fit. Blank spaces in CHAR and NCHAR fields are removed, and storing ANSI values in Unicode fields can yield up to 50% compression, depending on language and collation settings. Page compression explained. Page compression is more complex. It starts with row compression, then applies prefix compression by finding common values in columns and using anchor values. Finally, dictionary compression replaces repeated values with references to a dictionary stored at the start of the page. This process only happens if at least 20% space can be saved. Real-world results. Turning on row compression saved over 400 megabytes, reducing table size to 2.6 gigabytes. Page compression pushed savings further, dropping the table below 2 gigabytes, with query times remaining similar. Key takeaways. Compression can significantly reduce storage needs, but may slow down data manipulation. Choosing the right type depends on your data and performance requirements. Implementing high availability and disaster recovery for Azure SQL databases. Recovery time objective and recovery point objective are two crucial concepts in disaster recovery planning. While they sound similar, they serve different purposes and can even be opposites in certain scenarios. Key concepts: RTO versus RPO. Recovery time objective, or RTO, is the maximum time your system can be down after a failure before it must be restored. Recovery point objective, or RPO, is the maximum amount of data you can afford to lose, measured in time. These objectives are independent and must be considered separately. Real-world examples. Imagine using Google Docs with autosave. If your computer fails, it might take days to recover, but your document is safe, no data loss. That's a low RPO, high RTO scenario. Conversely, if you work locally without saving, a quick reboot could cost you hours of work, a low RTO, high RPO situation. Azure Database Tiers and SLAs. Azure's availability database service tiers offer varying disaster recovery features. For example, a service level agreement of 99.99% uptime still allows for over 50 minutes of downtime per year, which can impact your services significantly. Redundancy and compliance in Azure. Azure's availability zones and regions help ensure redundancy and compliance. Only the business-critical tier with Gen 5 hardware supports zone redundancy, providing robust protection for your data. Azure SQL Hyperscale is designed for massive scalability, supporting databases up to 100 terabytes in size. Its architecture is built to handle high availability and disaster recovery, making it a standout in the Azure SQL lineup. Architecture and scaling. Unlike traditional databases, Hyperscale separates its core functions. The database engine, page servers, and data files each operate independently. Page servers manage between 128 gigabytes and 1 terabyte of data, efficiently serving read requests and updating data through a dedicated log service. Backup and restore innovations. One of Hyperscale's most impressive features is its approach to backups. Instead of traditional full, differential, and log backups, Hyperscale uses snapshots of data files. This means backups are almost instantaneous, and even multi-terabyte databases can be restored in minutes, not hours or days. High availability and replicas. Hyperscale allows you to create secondary replicas to offload read operations. These replicas are updated from the primary node within milliseconds, offering a recovery point objective of 0 minutes and a recovery time goal of under 10 minutes. Limitations and final thoughts. However, Hyperscale does not support geo-replication. While you can restore a database to a new region, a data center outage could impact business continuity. Still, Hyperscale's architecture offers remarkable speed and flexibility for large-scale databases. When considering disaster recovery for on-premise databases, the cloud offers several solutions. Let's quickly explore 3 main options, each with its own strengths and limitations for keeping your data safe and available. One-way replication. First, there is one-way transactional replication to an Azure SQL database using publisher and subscriber technology. While this keeps an up-to-date copy of your data in the cloud, it lacks automatic failover and restore capabilities. This method is more suited for migrations with minimal downtime, not for high availability. All replicated tables must have a primary key. Data Sync Setup. Next is Azure Data Sync, which enables bidirectional replication between an on-premise database and Azure SQL using a hub and member design. To set this up, create a sync group in Azure, select a metadatabase, enable automatic syncing, and set your sync frequency. Install the Data Sync agent on your local machine, authenticate using a generated key, and register your databases. Once configured, you can select tables for synchronization, and data will flow both ways between your on-premise and cloud databases. Data sync limitations. However, data sync is not transactional and only allows synchronization every 5 minutes at most. It also does not support SQL-managed instance databases, which limits its flexibility. Failover group mention. Finally, failover group technology can be used for disaster recovery, either entirely on-premise or with a cloud-based virtual machine. Conclusion. Each solution has trade-offs, so carefully consider your organization's needs before choosing a disaster recovery approach for your on-premise databases.
Always-on availability groups are Microsoft's high availability and disaster recovery solution, designed to keep your SQL Server databases online, even during outages. Built on Windows failover cluster technology, they extend on-premise capabilities to the cloud using SQL Server on virtual machines. How availability groups work. Think of always-on as mirroring multiple databases at once. You have a primary database with read-write access and up to 8 read-only replicas. These replicas can be distributed across data centers and regions, providing redundancy and letting you offload read queries or backups to secondaries. Synchronous versus asynchronous commit. There are two main modes: synchronous commit, which ensures all replicas are fully up to date before confirming transactions, and asynchronous commit, which prioritizes performance but risks minor data loss. Choosing between them depends on your need for data integrity versus speed. Failover modes and scenarios. Automatic failover requires synchronous commit and healthy replicas, ensuring no data loss if the primary fails. Manual and forced failover options exist for planned maintenance or disaster recovery, giving flexibility in how you handle outages. Setting up and key requirements. Always-on availability groups require SQL Server Enterprise Edition, Windows Server, and Active Directory integration. Proper configuration, including cluster setup and firewall rules, is essential for seamless high availability and disaster recovery. Azure SQL provides redundancy and replication even outside its business-critical and premium tiers. Replication is asynchronous, meaning updates are not instant, and manual intervention is required for failover if a regional outage occurs. This ensures data protection across regions. Geo-replication and failover groups. With geo-replication, you can have up to 4 readable mirrored instances in different Azure regions. Failover groups, built on active geo-replication, allow a single endpoint for all replicas, simplifying connection management. However, automatic failover takes at least 1 hour, so for high availability and disaster recovery, manual failover is typically recommended. Setting up and testing replication. Setting up a failover group in the Azure portal is straightforward. Add a secondary server in a different region, migrate data, and confirm replication. Secondary databases are read-only, so you cannot write to them directly. Replication streams transaction logs, ensuring only completed transactions are copied. Key considerations and best practices. Always monitor replication lag using system tables. Secondary servers must match the primary in service tier. Use application intent equals read-only in your connection string for read-only workloads. Remember, read-only data may not always be fully up to date due to replication latency. Database backups are essential for protecting your data, especially outside of high-cost, business-critical solutions. Whether you are using SQL Server on-premises or in the cloud with Azure SQL databases or SQL managed instances, backups are your safety net. Backup types and schedules. In Azure, full database backups happen weekly, differential backups every 12 to 24 hours, and transaction logs are backed up every 5 to 10 minutes depending on your service tier and activity. These backups are stored in Azure Blob Storage in a different region, ensuring your data is safe even during a regional outage. Automation and Azure integration. On-premises or virtual machine users must set up backups manually using SQL Server Management Studio or automated jobs. You can schedule full, differential, and transaction log backups at intervals that suit your needs. Azure users can also back up directly to Blob Storage by creating credentials and selecting a URL as the backup destination. Point-in-time recovery. Restoring to a specific moment requires a combination of full, differential, and transaction log backups. In Azure, you simply select a restore point. On-premises, you restore backups in sequence, using options like with stop at to specify the exact time. Retention and cleanup. Backup retention is configurable. When a full backup expires, related differential and transaction log backups are deleted, ensuring storage is managed efficiently while maintaining recovery options. Implementing Azure SQL data security. Data exists in different states, each requiring its own protection strategy. Data at rest refers to information stored within a database file structure, untouched by the database engine.
If someone tries to access this data by bypassing the database engine's authorization, it is almost always for malicious reasons. Data in transit, on the other hand, is information legitimately accessed and transmitted across a network to a client application, such as a web or desktop program. Sensitive data, like medical records or credit card numbers, often requires restricted access, even among authorized users. Security layers. Protecting data involves multiple security layers, often visualized as an onion. The three outermost layers are crucial. Network security blocks unauthorized access to the entire database ecosystem, including the database engine, files, and data sent to client endpoints. Storage security safeguards the physical media where database files reside. Data security focuses on protecting the information within those files. These layers work together to shield data from both external and internal threats, ensuring only those with legitimate reasons can access sensitive information. Monitoring and assessment. A robust data security system must track changes, recording who altered what data and when. This audit trail is essential for accountability. Finally, regularly assessing your data protection mechanisms ensures they remain effective, helping you understand exactly how well your data is secured against evolving threats. Managing network access in Azure SQL is all about controlling who can connect to your databases. This process uses firewall rules, which are different for Azure SQL databases, SQL Server on-premises, and Azure SQL managed instances. Firewall rules in Azure SQL. In Azure SQL, there are two types of firewall rules, server level and database level. When a connection request comes in, database level rules are checked first. If the IP address is not allowed there, server level rules are checked next. For most users, it is best to set database level rules for specific access, following the principle of least privilege. Server-level rules are generally reserved for administrators or connections needing access to all databases. Both types allow up to 128 rules each. Configuring firewall rules. You can set server-level firewall rules through the Azure portal, but database-level rules require SQL commands. For example, use the stored procedure sp_set_firewall_rule to add a rule. Remember, rules are defined by IP address ranges, not single addresses, even if you only allow one. Managed instance connections. Azure SQL managed instances use virtual networks for access control, not firewall rules. You can connect using Azure VNet peering, VPN gateways, or ExpressRoute for secure, high-speed connections from on-premises networks. When you create a virtual machine or managed disk in Azure, you have encryption options. The default is encryption at rest with a platform-managed key, but let's explore how to implement encryption using a customer-managed key for greater control. Creating the key vault. The first step is to create a key vault to securely store your encryption key. When setting up the key vault, you can enable Azure Disk Encryption for volume encryption under Access Policy. If your key vault already exists, simply update the access policies under Settings to allow Azure Disk Encryption. Setting up the key and disk encryption set. Within the key vault, generate or import a key, like the example key named disk key. Next, create a disk encryption set resource. Make sure your disk encryption set, key vault, and the disk itself are all in the same region. Assign a resource group, then select your key vault and key. If you haven't created them yet, you can do so during this step. Assigning permissions and final steps. Once your disk encryption set is created, grant the necessary permissions. If you miss this step, you can always add an access policy later. Now, associate your disk with the disk encryption set using the Customer-Managed Key option. Automation options. You can also automate this process using PowerShell or Azure command line interface scripts, such as set as disk key encryption key or set as VM disk encryption extension.
When working with Azure SQL and SQL-managed instances, you do not have direct access to the underlying hard drive. This is why encryption is handled differently, using a method called transparent data encryption, or TDE. How TDE works in Azure SQL. Transparent data encryption encrypts and decrypts database pages in real time, as they are written to or read from long-term storage, such as the disk. This process ensures that your data remains secure at rest, without requiring manual intervention. Managing encryption keys. By default, all Azure SQL and SQL-managed instance databases use transparent data encryption with a service-managed key. For Azure SQL, this key is set at the server level, while for SQL-managed instances, it is set at the server instance level. However, you have the flexibility to switch from a service-managed key to a customer-managed key if you prefer, more control. Setting up customer-managed keys. To use a customer-managed key, navigate to the server's security settings and select Transparent Data Encryption. Here, you can choose your key from a vault or enter its URL. Azure will automatically grant the necessary permissions for your selected key. Key Vault and Access Policies. If you check your Key Vault's access policies, you will notice a new Database Monitor policy with permissions to get, wrap, and unwrap keys, ensuring secure management of your encryption keys.
Column encryption in SQL Server helps protect sensitive data by encrypting specific columns in your database. This feature is available in Azure SQL, Managed Instances, and SQL Server, and can be managed through SQL Server Management Studio. Setting up the Key Vault and Access Policy. To start, create a new key in Azure Key Vault, which will be used for encryption. It is crucial to set up an access policy for the identity that will access the Key Vault from your database server. The access permissions must include get, list, unwrap key, wrap key, verify, and sign. Creating master and encryption keys. Once the access policy is saved, open SQL Server Management Studio. In your database, expand Security, then Always Encrypted Keys. Right-click on Column Master Keys to create a new master key, selecting Azure Key Vault as the key store. Sign in with the identity that has the required permissions, choose your Key Vault, and select the key. Encrypting columns in SQL Server. Next, create a column encryption key, linking it to your master key. To encrypt a column, right-click the database, select Tasks, then Encrypt Columns. The wizard allows you to encrypt columns from multiple tables at once. Final steps and observations. Select your encryption key, choose Deterministic Encryption, and proceed. After encrypting, you will notice the encrypted column's data appears much longer than its original type, such as n-varchar10. This process is identical for Azure SQL databases. Azure SQL's advanced data security brings powerful tools to protect your data. With managed instances in Azure Synapse Analytics, you can classify data by information type and sensitivity and assess vulnerabilities. Vulnerability Assessment. Start by setting up Vulnerability Assessment in the Azure portal. Assign a storage account for reports, then scan your database. The assessment highlights security strengths and weaknesses, with results downloadable as Excel or JSON files for deeper analysis or integration. Data Discovery and Classification. Azure's Data Discovery service automatically suggests information types, like contact info or financial, and sensitivity levels, such as confidential or highly confidential, for your database columns. You can accept, adjust, or add classifications to ensure accuracy, tailoring protection to your needs. Auditing sensitive data access. Enable auditing to track who accesses sensitive columns. Send audit logs to storage, log analytics, or event hubs. With dashboards, you can see exactly which confidential fields have been accessed, supporting compliance and security monitoring. Dynamic data masking.
Dynamic data masking lets you partially hide sensitive data, like showing only the last 4 digits of a credit card. Set up masking rules in the portal, choosing from preset or custom formats for each column. Tracking changes in database tables is essential for understanding how your data evolves over time. While you could use update and delete triggers to log changes, Azure SQL Managed Instances and SQL Server offer a built-in solution called System Versioned Temporal Tables. Temporal here refers to time, not to be confused with temporary tables. Setting up System Versioned Temporal Tables. With System Versioned Temporal Tables, you associate a history table with your main data table. Both tables must have the same structure, including specific datetime to columns and an integer primary key. You have 3 options for creating the history table: create it automatically with a new data table, generate it for an existing table, or link an existing history table. The key columns, often named sys_start_time and sys_end_time, must be set as row start and row end and used as parameters in the period for system time. How system versioning works. Once system versioning is enabled, the database automatically logs historical versions of records whenever updates or deletions occur. You can also specify how long to retain history, which helps manage storage as the history table can grow quickly. Demonstration example. For example, after setting up a system-versioned customer table, updating a customer's name will automatically store the previous value in the history table. This makes tracking changes seamless and efficient. Many applications still rely on separate database authentication, often for historical reasons. But Azure Active Directory, or Azure AD, changes the game by centralizing user authentication and management, offering authentication as a service for modern organizations. What is Azure Active Directory? Azure Active Directory allows users to authenticate once, eliminating the need to remember multiple usernames and passwords. For administrators, it means managing just one credential per user and having a single place to control access, making life much simpler. Role-based access control explained. A key concept in Azure AD is role-based access control, or RBAC. RBAC assigns specific tasks to roles, which are then given to users. Each role defines permissions like read, write, or administer over Azure resources. Think of a role as a named group of permissions. Azure built-in roles. At the top of the RBAC hierarchy is the subscription owner, who has full control. Azure also provides built-in roles for Azure SQL, such as SQL DB Contributor and SQL Managed Instance Contributor, which let you create and manage databases and instances. Managing access and security. RBAC operations can be performed through the Azure portal or command line interface. While Azure AD and RBAC control access to servers and databases, Azure SQL's own security features manage access within the database after authentication. Let's walk through how to set the Active Directory admin on an Azure SQL server, a key step for secure and flexible database management in the cloud. Creating the Azure SQL database. Start by creating a new Azure SQL database. Choose your resource group, then create a new server. During setup, you'll define an SQL login and user, similar to the system admin account on traditional on-premise SQL servers. For this example, the admin login is named Azure User. Adjust compute and storage settings as needed, and select No Public Access for added security. Configuring firewall and access. Once the database is created, configure firewall settings. Allow other Azure services to access the resource and set a firewall rule for your local PC. Save these changes to ensure you can connect securely. Setting the Active Directory admin. Next, set up the Active Directory admin. Under Server Settings, select Active Directory Admin and click Set Admin. Choose a user from your Azure Active Directory, such as Halimad, and save. Using an admin group for best practice. For better management, create a security group in Azure Active Directory called SQL Admin. Assign users, like Lorilog, to this group. Then, set the group as the server admin. Now, any group member can authenticate securely. Managing access in Azure Active Directory is all about giving users just the permissions they need. Not everyone should be an admin, so let's see how to create ordinary users and assign roles in Azure SQL databases. Creating a contained user. First, log in as the SQL admin and create a new database, like another DB. To add a user such as Halimad, create them as a contained user within another DB. This means Halimad only exists in that database and cannot access others on the server. Assigning roles. To let Halimad read data, add them to the DB_data reader role using the SP_add role member procedure. If you want to give more permissions, like creating tables, add Halimad to the DB_owner role. Each role controls what the user can do. Now, create a new Active Directory user, Halam SQL, and add them to a group called Another DB Access Group. Log in with multi-factor authentication, set a password, and then associate the group with another DB as a contained user from the external provider. Managing group access and removing roles. Assign roles using the alter role statement. To remove a user from a role, simply use alter role drop member. This keeps your database secure and access tightly controlled. A managed identity in Azure lets resources securely authenticate with each other using tokens, eliminating the need for passwords. For example, a web app can connect to an Azure SQL database without storing credentials. Creating the web app and assigning identity. First, create a basic .NET Core web app in the Azure portal using default settings. Once deployed, assign a managed identity to the web app using the Azure Command Line Interface, or CLI, with the AZ Web App Identity Assign command, specifying the resource group and app name. Setting up Azure Active Directory group. Next, create an Azure Active Directory group called Another DB App Access. Assign the web app's managed identity to this group using the AZ group member add command. You can verify group membership and note the app ID and object ID for reference. Granting database permissions. Now, grant the managed identity access to the Azure SQL database. Create a contained user named DBAuth web app and give it read and write permissions on the target database. You can confirm the user's presence under database security settings. Testing managed identity authentication. Finally, update the web app's connection string to remove the password. When refreshed, the app successfully retrieves records from the database, proving that managed identity authentication is working securely and seamlessly. When a new user is created in a database, they can connect, but they cannot actually do anything until they are granted the right permissions. That is where database roles come in. Assigning permissions. To let a user read data from a table, you can assign them to the database data reader role using the stored procedure called SP_add role member. If you want them to write data, you might consider the database owner role, but that is often more access than needed. Overview of key roles. Database roles act like user groups with predefined permissions. The database owner role can do almost anything in the database except server-level tasks. However, for inserting, updating, or deleting data, the database data writer role is sufficient. The database access admin role manages who can access the database, while the database security admin role controls permissions for roles and objects.
The database backup operator role allows members to back up the database, and the database DDL admin role lets members make schema changes. Special roles and their functions. There are also deny roles, like database deny data reader and database deny data writer, which specifically block reading or writing data. The public role. Every user belongs to the public role, so assign permissions here for actions everyone should be able to perform. The principle of least privilege is a foundational security concept. It means users should only have the minimum access and permissions necessary to do their jobs. Think of it as the digital version of the need-to-know rule you often hear about in spy movies. Real-world scenarios. Consider an organization with 1,000 users. Most just need to read data or update a few tables, while only a handful require broader access. In one scenario, the database administrator gives everyone full access, making every user a database owner. In another, access is carefully tailored. Only system administrators and select users have elevated privileges, while the rest have limited rights to just the tables they need. Security implications. With full access for all, any breached account gives a hacker total control. But if least privilege is enforced, a hacker would need to compromise specific high-level accounts to gain the same power. This drastically reduces risk, especially since many breaches actually come from within an organization. Importance of role-based access. Setting up access by job role takes effort, but it is essential. Database roles let you assign precise permissions, ensuring users only see and modify what they truly need. Database permissions and roles are essential concepts for anyone working with databases. Understanding how they work helps you control who can access, modify, or manage different parts of your database. What are permissions and roles? Permissions, sometimes called privileges, determine what actions users can perform on database objects like tables, views, or stored procedures. These actions include reading, inserting, updating, deleting, creating, or dropping objects. Roles are collections of permissions that can be assigned to users, making it easier to manage access for groups rather than individuals. Granting, denying, and revoking permissions. Permissions can be granted, denied, or revoked. For example, you might grant a user the ability to insert data, but deny them the ability to update it. If you change your mind, you can revoke a permission, which removes any special access or restrictions previously set. Roles in action, a practical example. Suppose you create a user named Halamed and assign them data reader and writer roles. You can deny Halamed permission to update a specific table, then later revoke that denial or grant update permission through a new role called special role. Summary. Managing permissions and roles ensures your database remains secure and users have the right level of access for their tasks. Managing SQL Server permissions does not require memorizing complex SQL statements. With SQL Server Management Studio, you can use a graphical interface to create logins, assign roles, and set permissions, making the process more intuitive and visual. Creating a new login. Let's walk through an example. First, create a new login named Whom. Choose SQL Server Authentication and set a simple password, making sure to uncheck the Enforce Password Policy option if the password is too basic. Set the default database to Lorilog. Assigning roles and permissions. Next, map the Whom login to the Lorilog database. By default, the DB owner role may be assigned, but you can uncheck it and instead grant data reader and data writer roles. This limits the user's access to reading and writing data without full administrative control. Testing permissions as the new user. After setup, log in as Whom. You will see access only to the Lorilog database.
Selecting from the new table works, but inserting new records is denied, as expected. Updates are allowed, reflecting the assigned permissions. Column-level permissions. You can also set permissions at the column level. For example, deny select permission on the ID column for whom. Now, when selecting data, the ID column is hidden and only permitted columns are visible. Azure SQL. Designing and implementing a migration plan. Migrating a database is a journey that starts with your current environment. Whether you are moving from a Windows-hosted SQL server or a less compatible system, your starting point shapes the complexity of your migration. Assessing your starting point. Understanding your existing database environment is crucial. This means looking at all connected systems and determining which databases can move to the cloud. Sometimes certain systems must remain on-premises, leading to a hybrid setup. Not every on-premises database has a direct equivalent in Azure SQL, so some databases can be transferred as they are, while others may need refactoring or modifications to associated systems. Planning the migration. After assessing your environment, design your target setup and plan the migration. The type and structure of both your source and target environments, the volume of data, and your tolerance for downtime all influence your migration strategy. Executing the migration. The actual migration process depends on your assessment and planning. It involves transferring and transforming data, adapting systems, and meeting specific business requirements to ensure a smooth transition. Support and resources. Microsoft and Azure offer a wide range of resources, including tools, online services, consulting, and extensive documentation to support you at every stage of your database migration journey. When migrating databases to the cloud, two main scenarios come into play: rehosting and replatforming. Each approach has its own benefits and challenges, and understanding the differences is key to a successful migration. Rehosting explained. Rehosting, often called lift and shift, involves moving your on-premises database to a virtual machine in the cloud, such as an Azure virtual machine. This method is flexible, allowing you to use Microsoft, Azure, or third-party tools to complete the migration. It is especially useful when your database relies on custom or third-party software libraries, or when you want minimal changes to your existing setup. Replatforming explained. Replatforming means migrating to a different database engine or a managed service like Azure SQL, Azure MySQL, or Azure PostgreSQL. Unlike rehosting, you cannot simply back up and restore your database. Instead, you might export your database to a backpack file and import it into Azure, which requires more planning and adaptation. Downtime and migration strategies. One-time migrations can cause downtime. To minimize this, you can migrate slow-changing data first, then switch over the frequently changing data during a shorter downtime window, especially for transactional databases. Zero downtime options. If downtime is unacceptable, options like failover clustering for SQL Server can synchronize data in real time. For non-SQL Server databases, explore high availability or replication solutions from your database vendor. When it comes to data migration, whether you are rehosting or replatforming, physically moving your data is unavoidable. The method you choose impacts speed, cost, and reliability, so let's break down your options. Physical data transfer. If you have a massive amount of data and speed is not a priority, sending a physical copy using Azure Databox could be a cost-effective solution. With Azure Databox, you mail an external hard drive to Microsoft, and they upload your data to your online storage. This process takes at least 2 weeks, making it unsuitable for live migrations, but it's ideal for testing new systems under production loads. Virtual network transfers. For most organizations, a virtual network is the preferred choice. Setting up a site-to-site connection is quick and flexible. You can add or remove VPN connections as needed, allowing you to test migration scenarios and minimize downtime during the live cutover. Calculating your data volume and available bandwidth helps estimate migration time. ExpressRoute, the premium option. ExpressRoute is the gold standard for on-premises to Azure connectivity. It offers high bandwidth, stability, and built-in redundancy. While setup takes longer and scaling down is not possible, you can combine ExpressRoute with VPNs for extra flexibility. Azure Migrate is a suite of tools designed to help you assess and move your on-premises infrastructure, software, and data to the Azure cloud. It streamlines the migration process, offering tailored recommendations and cost estimates for your unique environment. Infrastructure assessment. To evaluate your physical or virtual servers, Azure Migrate provides a downloadable appliance as a virtual machine image for VMware or Hyper-V. If deploying a dedicated assessment virtual machine is not feasible, you can use a spreadsheet template to manually input server details and upload them for analysis. Database assessment. For SQL Server databases, Azure Migrate offers 2 main tools, the free Microsoft Data Migration Assistant, or DMA, and the paid Unify Cloud Cloud Pilot. DMA checks compatibility and can migrate databases but does not support Amazon Web Services relational database service for SQL Server as a source. Migration tools. The Data Migration Service, accessed through the Azure portal, migrates SQL Server and non-SQL databases to their Azure equivalents. Microsoft SQL Server Migration Assistant supports migrations from Access, DB2, MySQL, Oracle, and SAP ASE, with MySQL tools often working for MariaDB. Application Layer and Guidance. The Data Access Migration Toolkit, a Visual Studio Code extension, analyzes application code for embedded SQL. Azure Database Migration Guides provide step-by-step documentation for various migration scenarios, ensuring a smoother transition to Azure. Migrating your database to Azure is a big decision, and the first step is understanding your options. The main factor is whether you are changing your database server or keeping the same system in the cloud. Migration scenarios. If you are moving from an on-premises SQL Server to SQL Server on an Azure virtual machine, that is called rehosting or lift and shift. But if you are switching to a different Azure SQL variant, like Managed Instance or Azure SQL Database, you are re-platforming. Changing the database engine means you must check compatibility, including data types and external dependencies. Assessment tools. Azure Migrate Discovery and Assessment evaluates your current servers and recommends Azure virtual machines, even estimating costs. The Microsoft Data Migration Assistant checks if your SQL Server is ready for Azure, highlighting any features or data types that need attention. For deeper analysis, the Data Experimentation Assistant and Data Access Migration Toolkit help assess workloads and embedded SQL statements. Migration strategies. Minimizing downtime is key. You might migrate static data first, then synchronize fast-changing data. If zero downtime is required, data replication keeps both systems in sync for a seamless cutover. Migration tools. Microsoft offers Data Migration Assistant, Data Migration Service, and SQL Server Migration Assistant to help you move your data efficiently to Azure.
Hello and welcome to this new video. In this video, we're going to cover some important real exam question answers for DP-300,
Now,
which is
let's dive
Microsoft
into the
Azure
latest
Database
real exam
Administrator
questions and
Associate
answers
Certification
for the
exam.
Microsoft Certified
So before going to the question
DP-300
answers, we
exam.
request you to
If
kindly
you haven't
subscribe to our
subscribed
YouTube
to our
channel if you're
YouTube
not
channel
already a
yet, we'd
subscriber.
love for you to join our
And these
growing
question answers
community.
PDF is
Just
also
hit that
available to
subscribe
download
button.
from
Want a downloadable PDF
shapingpixel.com
of these
website. The
questions
full
and
link will
answers?
be in the
You can grab
description.
it from our website,
So each question in this video will be played for 1 minute
www.shapingpixel.com.
without
Full
sound.
link is in the
If you think
description
it's too
below.
slow or fast,
Let's get
use the
started.
YouTube video settings to slow down or fast forward the video. Let's jump on to the questions.
Thanks for watching. If you haven't subscribed to our YouTube channel yet, we'd love for you to join our growing community. Just hit that subscribe button. Want a downloadable PDF of these questions and answers? You can grab it from our website, www.shapingpixel.com. Full link is in the description below. Happy learning!